All right, so what we're going to talk about, if you remember back on Friday, I gave you that handout, that Word document that asked you in the coordinate plane to prove that a quadrilateral is a parallelogram. And the only tools that you had to do that were slope, right? So you had to address the definition of a parallelogram, or make sure that your shape held the properties defined in the definition. Today we're going to learn some theorems that allow us to prove that a quadrilateral is a parallelogram using alternative routes. Instead of just saying, well, both pairs of opposite sides are parallel, that's a parallelogram. These are going to be facts that we can figure out that will eventually lead us or will force opposite sides to be parallel. Okay? But not directly trying to use slopes. Does that make sense?
Yep.
Okay? We might use one pair of opposite sides to be parallel and one pair of opposite sides to be congruent. And then the byproduct of that will be that actually both sets of opposite sides are parallel, okay, which meets the definition of a parallelogram. So I guess the first theorem we'll talk about is this. Okay? If you remember, the first theorem in section 6.2 said if you have a parallelogram, then both pairs of opposite sides are congruent. Here, it reverses that statement or finds the converse of that statement. It says if both pairs of opposite sides are congruent, then the then the quadrilateral is a parallelogram. So here, we're starting with a generic quadrilateral. We're able to learn that both pairs of opposite sides are congruent, and it allows us to reclassify it better, no longer as a generic quadrilateral, but as a parallelogram. A special kind of quadrilateral. And there you see at the bottom, I don't know if you need to write that, but it says this should make sense because we know from 6.2 that in a parallelogram, opposite sides are congruent. It's good. Any ice cream? Well, some mint chocolate chip, yeah. Mint chocolate chip? You're kidding me, right?
Have you ever had strawberry banana?
Yeah, I like strawberry.
Strawberry and banana.
I mean, I could take or leave the banana.
It's the best.
Have you ever eaten mint chocolate chip ice cream?
Yeah, I don't like it.
Get out.
I like
Get
the
out.
taste of it, but I don't like how hard the chocolate chips get.
You big sissy.
I don't like it. I don't like the idea of just putting kind of first. Like, we have strawberry in the middle.
All right, so what we're talking about here, if I were to take a segment, let's AB, and a segment, guys, come on. All right, so if I take those two segments, would you agree that those could be two sides of a quadrilateral? All right, I'm going to take and ask this to create a third segment with a vertex at C, but I want it to be the length of AB. I don't know if that's going to do it. Yeah. All right, so that one there is the one that is opposite AB, right? If I look at the distance of these two things, that distance and that distance, they're the same, correct? Okay. Now I want to do the same thing over here at B, but I want to make that length AC. Would you agree that that blue distance is the same as that blue distance? Okay, but do I have a polygon right now? No. Okay, so the only way that I can make a polygon is to make these things touch, right? So let's see if I can make E, I think it's got to go there, and D go there. Okay, so the only thing that I've done, think about this, the only thing that we've focused on was forcing both pairs of opposite sides to be congruent, right? Well, when you do that, a byproduct of that Okay? I'm going to delete the distances out of here, just so it cleans up a little bit. We don't have a whole lot of values on here. But since the blue ones are the same length, and so are the red ones, what do we see about the slopes of the blue ones then? They're the same. So if the slopes of the blue ones are the same, the blue ones are parallel. What do you see about the slopes of the red ones? They're both the same, right? So, by looking at just both pairs of opposite sides being congruent, what falls out of that is that it forces both pairs of opposite sides to be parallel. And if both pairs of opposite sides are parallel, what did we just create by definition? A parallelogram. Okay? And that's going to be the case 100% of the time. Okay? If you're able to see that both pairs of opposite sides are congruent, then you have a parallelogram. So if I were to go back to what I asked you to do on Friday, and you were told to prove that's a parallelogram, and then find all the distances, you had to do that on Friday by finding all the slopes first. See, that was a parallelogram. Then you went through the distance formula, right? What this theorem is saying is that you don't have to do that. If your end all task was to find all four side lengths, if you can do that, and then you can recognize that, well, two pairs of these are the same, doesn't that automatically tell you it's a parallelogram and you don't even have to do the slopes? Does that make sense? So our theorem should allow us to kind of maybe abbreviate some of the algebra that we have to do in trying to prove a shape to be a parallelogram. Here's another one. Another reason why a quadrilateral can become a parallelogram. So if one pair of opposite sides of a quadrilateral are both congruent and parallel. So just one pair. Don't even care about the second pair. Just one pair is congruent, and that one pair is parallel. That will make a parallelogram. Could, because a square is a parallelogram. Yep. The Bears. Yeah, I still want them to win. I wanted the Saints to win, and I wanted the Chiefs to win. I was hoping. I don't really like Los Angeles, but I really hate New England, so I didn't really care who won that game. Who's the other game? Oh, Rams and the Rams play Cowboys. I hate the Cowboys, but I don't like the Rams either. Not a big fan of Los Angeles in general. I can't stand the Cowboys because they make me watch them every single Sunday. They're on every Sunday. They're on TV. All right. One pair of opposite sides of a quadrilateral are both congruent and parallel, and the quadrilateral is a parallelogram. What's going on there is this idea. How do you create segments that are parallel? They have to have the what? Same slope, okay? What is the slope from A to B here? Okay, so it's 1/2, right? It's up 3 over 6. So if I make a segment that has a slope of 1 over 2, so that segment right there, is that segment going to be congruent to what I already have up there? The slopes are the same, right? So they're parallel, but they're not congruent in length. So instead of using 1/2, what should I use if I want to make them the same in regards to distance? 3/6. If I go up 3 over 6, hopefully I went over 6. 1, 2, 3, yeah. So that gives us both of those to be parallel, right? And would you agree that both of them are congruent? Okay. So if I do that then, let's look at that segment there and that segment there. What is a byproduct of the solid ones being congruent and parallel? What happens with the dotted ones? What would you agree with the dotted ones? They're congruent, right? Okay. But they're, and in regards to meeting our conclusion, are they parallel? Yes. Okay. And no matter what, if I look at this, put all these values up here. So the slope up on that one, slope on that one again, and distance there, distance there. No matter where I move, these solid blue lines, are they parallel and congruent? Does that make them the dotted ones always parallel as well? Yeah. Okay. So no matter what, if you have two segments, and they're opposite, they're opposite segments of a quadrilateral, parallel and congruent, then the other two segments are forced to be parallel as well, and now you've got two sets of parallel lines, right? And then that meets the definition of being a parallelogram. Okay. If both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Both pairs of opposite angles congruent, then the quadrilateral is a parallelogram. What's happening here is we are defining or laying out the properties that we're going to use inside the coordinate plane here pretty soon to show whether a set of 4 points produces a parallelogram or not. Okay? And based off of maybe information that we already have or information that's being provided in the problem, it might make more sense to maybe use this theorem than the previous one. Okay? Or maybe it makes more sense to use the previous theorem over this one. Okay? When we're working in the coordinate plane. And to be honest with you, when we're working in the coordinate plane, it's very difficult at this juncture to deal with angles. Okay, and to do the algebra that provides this angle measurement. So usually we'll talk about distance and slopes. Yeah. So both pairs of opposite angles of a quadrilateral are congruent, and the quadrilateral is a parallelogram. This one's kind of hard to set up. Okay, but I'll show you in GeoGebra the kind of the best way of viewing this. Yes?
Andrew, wash your hands. Okay, good.
You got issues.
I'm gonna wash my hands. I don't.
All right, so if I've got that angle there, okay, now I'm going to put in that angle there. Are those angles congruent? No. Okay. So let's kind of move these around so that they do become congruent. 61, let's see here, 52 point. Okay, they're congruent right there, right? Are they opposite? Okay. Let's see what this angle up here is. That angle, 127.235, this one here, $127.235. You guys okay with that? Okay. So those are both pairs of opposite angles are congruent. So now if I were to look at that shape right there, okay? Both pairs of opposite angles are congruent. What is that shape? Yeah, because that slope right there, now you can't see, it's that slope is negative 0.4. This slope here, again, negative 0.4. This slope here, 0.6. This slope over here, 0.6. Does that make sense, everybody? So just by looking at the angles and forcing the angles to be opposite and congruent, both pairs, it automatically makes the slopes that are opposite, makes them congruent slopes or equal slopes. If I were to, let's just kind of move point E. Did that mess everything up? Are both pairs of opposite angles, so is that angle 78.69, is that different than 52.76? Yes. So if they're different, can it be a parallelogram? Now, you see, obviously, that quadrilateral there is not a parallelogram, right? Okay. But probably not even a kite. Let's say that so we move all of these, okay? When I do that, are opposite angles still remaining congruent? Yep. So is that maroon quadrilateral always still a parallelogram? Yeah. Okay. Now, in addressing this theorem and using this theorem in the coordinate plane, that's very hard because we have trouble finding out what our angle measurements are right now because we haven't talked about sine, cosine, and tangent yet. Okay. This is another one. This one's hard to show, and I'm not going to show this one on GeoGebra. I'll just show it with the picture here. So if an angle in its supplementary, or if an angle is supplementary with both of its consecutive angles, then the quadrilateral is a parallelogram. So again?
Not basically throwing off what we did before. Well, because they're both supplementary.
Yeah, it kind of, yeah. I see what you're saying. What this one is doing, though, is going back to chapter 3. If I have this line right here, AB, and this line right here, I don't know, there's probably a point D down here. If I look at those two lines, are they being cut by AC? Or is AC intersecting them? So would AC be called a transversal? Well, if this angle A and this angle C, which are consecutive, correct?
Yep.
If they're supplementary, what's that tell us about these solid blue lines? They would be parallel, right? So if I'm able to show that, okay, that tells me that right now I've got one pair of opposite sides parallel. So it takes my quadrilateral and by definition makes it a trapezoid now. Okay? Well, we need both pairs of opposite sides to be parallel, right? Well, then what we do is we say, okay, well, let's look at that solid red line, this solid red line, and now AB is being my transversal. Well, if AB is my transversal, isn't that angle there, which is consecutive to that one, if those are supplementary, what's it tell me about the red lines? They are parallel. And if the red ones are parallel, we now have parallelogram. Red ones are parallel, blue ones are parallel, we got a parallelogram. Okay? So when both pairs of, or when two sets of consecutive angles are supplementary, then we get a parallelogram. We use that theorem here in an example in a moment. The last one. Last theorem for the day looks like this. Let's take a segment and find that segment's midpoint. Okay, so it does a good job here. And I'm going to manipulate a little bit so it looks like that. Can I find another segment? Let's just make that other segment straight up and down. Can I find its midpoint? Okay. And let's just color this one. Okay. If I were to do this, so those two midpoints, F and C, land on top of each other, would you guys make the argument that the red segment is bisecting the blue one? It goes through the blue one's midpoint, right? Is the blue one bisecting the red one? Because it's going through the red one's midpoint, right? So those two segments bisecting each other. Okay. What segments of a parallelogram have to bisect each other? That we talked about last week. The diagonal. So right there, I have created diagonals of some parallelogram. Okay? So when I do this, do these endpoints of these segments, do they create endpoints for your segments of your parallelogram. Okay, now look at AD. What kind of segment is AD? It goes straight left to right.
A line segment.
It's a line segment, but it's, what word do you use?
Oh, it's a horizontal.
Horizontal. So AD is horizontal, EB is horizontal, right?
Yep.
They are by definition, any two horizontal lines are parallel, right? So we know they're parallel. If I find their slope, it should say 0. Slope 0, slope 0. That one, slope of negative 4/3. Negative 4/3, right? Okay. So are those two parallel? Okay. So think about what happened here. All we focused on was making sure those diagonals bisected each other. And if those diagonals bisect each other, what was the end result? Those four segments, opposite segments, were parallel. Therefore, you reach the conclusion of a parallelogram. Okay, so I'll give you that theorem written out in a concise manner. It says if the diagonals of a quadrilateral bisect each other, meaning the blue one bisected the red one bisected the blue one, right? If that happens, you always get a parallelogram. If I don't have creamer. French vanilla, international delight. So I want to drink.
I don't drink.
Because I drink coffee for the creamer.
I don't drink coffee because I can't drink coffee with cream or sugar in it. I've only ever been able to drink black coffee.
Yeah.
I don't like any other coffee. That's my dad.
Coffee's getting expensive. I'm gonna have to stop drinking it.
I get cappuccinos that price.
So you're still writing? So all the coffee trees in South America are getting a disease that's inhibiting their growth and their bean production. And at the same time, there wasn't enough foresight to realize that these trees that we all planted 100 years ago are going to mature, and at some point they stop producing fruit, which would be the beans. So the coffee industry is losing thousands and thousands of trees. So coffee that I spent, I use Keurig, you can buy a 12-pack for, when I started drinking coffee, I could buy a 12-pack of coffee for $4. Now they're $11. It's just gone from a 50 cents a cup to $1.20 a cup. I'm gonna have to either get another job so I can address my addiction in the right way, or just stop drinking coffee. All right, so if I look at this one, okay, here we're trying to figure out what x and y have to be so that we can have a parallelogram. Well, we don't have the ability, when we're seeing problems like this, we don't have the ability to find the slopes of those segments because we're not in the coordinate plane, right? So we have to use these theorems. What did one of these theorems say about that side compared to that side? They had to be what? Congruent. So can I say 3x minus 5 equals 2x plus 1? All right? That same exact theorem, so if I do that, that's not enough to make that a parallelogram, right? Okay? Those other sides could still, this side could be smaller and this side could be longer. Okay, so PX could be smaller, QR could be longer, and it would not be a parallelogram. The theorem said that and that had to be the same as well, right? Those two equations need to be true so that shape becomes a parallelogram. Well, those two equations are only true when x is what value? When I solve that first equation, what is x going to be? X is going to be 6. And in that bottom equation, y is going to be 8. So when I use those two values in this problem, those are the only two that are going to force that shape to be a parallelogram. Those are the only two that are going to force both pairs of opposite sides to be congruent, right? And when both pairs of opposite sides are congruent, we saw that by a byproduct, the opposite sides become parallel. It becomes a parallelogram. Okay? Okay. So that's just using one of those theorems in a direct fashion to solve an algebraic problem. We're going to do it again here with this question in this slide, but now what are we talking about? What objects are we talking about? You got angles. And there were two theorems with angles. And what I want you to understand is that there's going to be a lot of different ways to solve this problem, but you have to use the full theorem, okay? So I'm going to look at angle E. What should angle E be equal to? Angle G. E and G are opposite, right? They have to be equal. 12x plus 7. Okay? That was saying that what we've said here is that angle and that angle are congruent. But the theorem says both pairs of opposite angles have to be congruent, right? So what's the other set? H and F. So y plus 10 has to equal 4x plus 13, right? Now, I'm not running out of time here, but I'm not going to solve that, but you have now a system that you solve for x and y, right? Okay? That's one approach. Is there another approach? Huh? That's not just supplementary. Okay? Which angle do you want to start at? Okay, angle H. So you say angle H. What does it have to be supplementary with? E and G, right? So H is y plus 10. We have to be able to add to it E, which is 3y minus 2, and that should be supplementary. Why would I like that equation better than anything I've already written up there? Only one variable, right? Okay. I can solve that one a lot easier. Now, so we're saying those two had to be supplementary. Well, if those two are supplementary, that only makes the top and bottom parallel, right? We need to make the left and right parallel as well. So H and G need to be supplementary as well. So y plus 10 plus 12x plus 7 needs to equal 180. Now, there's two variables, right? But in the equation above, we've already solved for y, correct? So I think using that approach is a little bit easier. Now, Alex started with H. Last class, we started with E. We said E and H had to be 180, and E and F had to be 180, right? Or you can start with G. G and H would be 180. G and F would be 180. Does that make sense to everybody? There's about 6 different ways you can set up equations to solve this problem. What I want you to make sure you understand is that you cannot use, so that one I got in the blue box, that was using opposite angles congruent, right? The one on the right is saying consecutive angles are supplementary. You cannot use half of this theorem that said opposite angles are congruent. So use that formula, and then maybe come over here and use that one, okay? Because that's half of opposite angles congruent. This one here is half of consecutive angles supplementary. Does that make sense? Yeah. Now, what will happen is you will get the right answer, but you've gotten to the right answer using wrong or incorrect logic. Does that make sense? Okay? Because we do not have a theorem that says one set of opposite angles congruent and one set of consecutive angles supplementary makes a parallelogram. Okay? It will work because it is indeed a parallelogram, but it's erroneous logic. Okay? Your homework this evening. No. You don't have to do anything on Math Excel tonight. We might do it in class tomorrow. But under section 6.3, there is a worksheet. So I'll show you where it's at. I'll also probably email this towards the end of the day. So 6.3, that link right there. Okay. So click on that, download it. That's your worksheet. Have your answers ready to be typed into Math Excel tomorrow during class. I don't know if we'll do it tomorrow. I might leave it open through tomorrow evening, but the earliest will be at the beginning of class tomorrow. Okay, so make sure you have that completed. Shouldn't be anything that's real taxing.